So good morning. I am Krishna Kumar from Krishna's classroom. We continue our explorations from where we left last time. So we were concerned about the construction of the Volterra's function. It's a beautiful example. In fact, the objective is the following. On the interval 0, 1, we construct a function, a continuous function, rather a uniformly continuous function because it's a compact interval, with the property that the function is uniformly continuous, it has derivative, it is a differentiable function everywhere, but on the at points of the Cantor set with alpha less than 1, the derivative of the function is unbounded. Now this is the problem. Okay. So it's defined all over 0, 1, it's a continuous function, it is differentiable function, the derivative exists everywhere, and you see that the derivative at C alpha, at points in C alpha, is discontinuous at points in C alpha. Now this is the important fact. And now what happens is, I said sometime earlier, there is an unbounded derivative. It's not unbounded, it's a bounded derivative, but discontinuous. The derivative is discontinuous at all points of C alpha. Further, you see that the C alpha has it's not a null set. If you compute let me use the term measure, although I have not defined it, but the content of that particular set, it is I guess something like length in the inverted commas 1 minus alpha, which is positive as long as you take alpha less than 1. Therefore, it is not a null set. Since it is not a null set, now you see that the function f derivative that you construct is not a Riemann integrable function. Now this is the objective. So we are actually looking forward to construct such a function. So we construct even with bounded derivative, which is discontinuous at points in C alpha. So f derivative is discontinuous C alpha, and therefore, and C alpha is not a null set for f. Although going through the process, and we constructed this function has been constructed by patching up different functions. Now we will explain how we patch up these functions to get the function defined on the interval 0, 1. So we have C alpha, the Cantor set with 0 less than alpha less than 1. This is the Cantor set. Now how to to define this function capital F. This is the problem. So, as a part of the brick by brick construction, we indicated how one would construct it over an open interval AB. What did we do? We picked the point and we constructed a function. See, we started with this function f a equal to x minus a whole square one upon x minus a, where x is not equal to a, and the function defined as 0 for x equal to a. From this, so this is your x. From this function, we constructed FAB. This is the graph of FAB. So we constructed FAB on the interval AB. This is a general interval A less than B. What we did was we chose the midpoint. This is the interval AB. We chose the midpoint A plus B by 2. Now we looked at FA defined here, because you know that it is bounded between x minus a whole square and minus x minus a whole square. Those are two branches that I have drawn here. And then you see that it is switched, it is given an oscillation with the sign, with the factor sine 1 by x minus a, and then you can see that you can find out where the function becomes 0, where the function has the maximum, etc., etc. All these are possible. What you pick up is a point alpha A, which is a supremum of the points where f derivative AB is equal to 0 and less than a plus b by 2. So it is lying between a and a plus b by 2, and this is the last point where f derivative AB is 0. In other words, the last point where either a maximum or a minimum appears for the function sine 1 by x minus a. That's what it is. So not sine 1 by x minus a whole square into sine x 1 minus a. Which means this is the point, the last point before a plus b by 2, where the tangent to the function becomes parallel to the x-axis. So this is how the alpha a is located, and this is defined by alpha a equal to supremum of. So I think I have put it down here. Alpha a equal to all x such that a less than or equal to x less than or equal to a plus b by 2, a plus b by 2, and f derivative x equal to b. This is the function that you, so this is the point that I define. Does it exist? I mean, it exists because it is bounded above. There's a sequence of points, as you can see. It is there. The supremum exists, and the supremum is denoted by some alpha a. Okay, and I have given a pictorial description of this. Now this is on the interval a to a plus b by 2. So this is the last point in this graph. where the tangent to the graph becomes parallel to the x-axis, and that I have denoted by alpha. And then what one does is, how FAB is defined up to this, you define it as FA. Then from this point on to its reflected point here, its reflection here, or even up to alpha a to a plus b by 2, that's easy to say. The function is defined as, now this is x equal to f of alpha. It's a constant function. And then what you do is, you have defined the function on the interval a to a plus b by 2. Just reflect the function about the line x equal to a plus b by 2 and get it. Then what happens? Once again you will see its reflection here. You get a symmetric function emerging like this, and I have given the graph of this function. So the graph of this function is, it oscillates violently at a or around a and around b. And then what happens is, it goes up to alpha a, and then you have the corresponding point for alpha a. So the distance to this point is, you see, the distance to this point from b is going to be equal to alpha a minus a. So this distance will be alpha a minus a. And then of course it's the mirror reflection of the function that you have. And then if you patch up, what happens is, in between these 2 points, the function is defined as fa f of alpha. It's a constant function, and then from then onwards the oscillating function is obtained. So it is now fully defined on the interval. This is the graph. Now let's see what more we can say about this function. First of all, you observe that this function is a continuous function. There's no doubt of it. Okay. The second factor is that this function has a derivative everywhere. Okay. And you see, these are the points where you may have some kind of a doubt. So you see that this point has been chosen such that f derivative of a equal to 0. Therefore, you have the new function that you have obtained on this, f of ab at alpha a equal to 0, and this is a constant function then onwards. Therefore, the derivative exists and the derivative is equal to 0. So on this part, the function has derivative 0, and from then onwards, this is not the definition of function. Because on the other hand, on this part, you see that again the function is well defined. It's a reflection of that. Its derivative exists and is continuous. X. Now what happens at the point A? At the point A, the function is continuous because of the modifying factor x minus a whole square. Okay, here it will be the similar thing happening at B. Whatever is happening here, there is a similar thing happening here. Secondly, if you differentiate, this is the derivative that you obtain. Okay. So if you take this function and differentiate it, this is what you get. And you see that once again, x minus a will take care of it at a, because this is a bounded function, therefore this term does not contribute at a. And at this point, what happens is, okay, look at the derivative. Yeah, how have we defined? The function is defined as 0 here at these 2 endpoints. So what about the derivative? You can easily compute that f derivative of a at 0 equal to 0. How do you do that? You take, this is actually f a x minus f a 0 divided by x. So the derivative exists at 0 and the derivative is given to be 0 j. There is no problem. But you see that the derivative when x not equal to a is given by this one, and you see that this is not continuous at the point x equal to a. Why? This term is fine because it goes to 0 because of the influence of this x minus a appearing here, whereas this one is an oscillatory term, so you just don't know, the limit does not exist. Okay. Therefore, in short, what happens is the FAT that you have defined is a very interesting function. It's continuous everywhere. Its derivative exists everywhere. But at these extreme endpoints A and B, the derivative is not continuous. Okay, so that is the construction. Now, having constructed this, we now go over to construct the function on the interval 0 to 1. Okay, so that's our next task. So, step 3. So I don't want to remove this picture because this picture is very handy. So I will start. Okay, let's do that. Now we have to have an idea of how this C alpha looks like. How this C alpha has been constructed. This is something which we should first look at. The C alpha that you have has been constructed in the following way. So we have the interval 0 to 1, and for some alpha, if this is half, you take a interval, an open interval, something like the diameter of the set is going to be alpha, symmetrically placed about half. So you see that this is actually half minus alpha by 2, and here it is half plus alpha. Remove this interval. Then what you have? You are left with the two closed intervals. Once again, you see the middle point. Remove something like alpha divided by 2 square. And so on. You keep removing small things from here around the middle, and then you are left with further. Oh, you go through the constructions like this and so on. Therefore, eventually, what you get a set of points which you call C alpha, and we have seen that C alpha is essentially the interval 0, 1 slash the union of minus 1 so we keep removing open intervals successively, and then what is left out on 0, 1 is called C alpha in that pattern. Okay, you don't have to worry what exactly the removed portions are. Then you also see that what you call the length of this one, or the length of the total length of the interval that you have removed is alpha. Therefore, you have what is left over is this. So the measure of content of C alpha, or length C alpha is 1 minus alpha. So it is not, so C alpha is not a null set. Not a null set. This is the inference that you have. Okay, as long as for alpha less than 1. This is what we have. This is the information that we have. Now what do you do? We define the function f as follows. So we define the function fx to be, okay, we define the function f of x to be equal to 0 for x belonging to C alpha. That means at all points in C alpha, we define the function to be 0. And you can see that these sort of points do come inside C alpha, and at all those points the function is defined to be 0. Now you can see what you do is you do the same thing over these leftover gaps. Because a lot of gaps will come, the gaps, the distance between the endpoints will get smaller and smaller, but they are all open intervals. So on the open intervals, you do what exactly you did here. So you see that you get such violently oscillating functions oscillating at the endpoints, and then the function with all these listed properties. So you define this as f. I write this as f a b x. If x belongs to I n minus 1 j, which is defined as the open interval. So AB is a generic term which corresponds to each one of these ij n minus 1. Okay. So for each one of that you define this, which means here you define it, here you define it, here you define it, again you take removing pieces from here, there also you define it, and so on, and patch up. So at these points which belong to C alpha, you see that the function is defined to be 0. So you see that by this definition you can actually show that the function you have defined is a continuous function on the interval 0, 1. So this is our strategy. It's a continuous, which is a differentiable function everywhere on 0, 1, with a bounded derivative which is discontinuous at the point C alpha. So that's exactly what we are up to. So let us start working on each one of this. Now this is for what you have is in j and 1 less than or equal to j less than or equal to 2. This is that, and then it's something very beautiful function. In fact, it's difficult to draw it, but you can imagine once you understand this function. Okay. Now let us start proving one by one. So if x does not C alpha, then capital F is differentiable. Differentiable, and f derivative at x equal to f derivative for some x with I Vj Lv which is contained in 0. So the problem is what happens when x equal to a or b, that means at the end points, which turn out to be essentially a point in C alpha. So we take now, let us investigate. Let x belongs to C alpha. For other places in university. So let x belong to C alpha. Eta positive, we are arbitrary. Now we estimate the derivative actually. So x is a point in C alpha. So we estimate this. Now you see, we have let y belong to 0. Y need not be in 0. Such that mod y minus x is less than eta. So it is in the eta neighborhood of the point x. That's what we have. So if y belongs to C alpha, then fy minus fx divided by y minus x, this is equal to 0 because both fx and fy are defined like it. I mean, y could be in C alpha because we are taking an interval of eta is arbitrarily chosen, and it's an eta neighborhood of x you are chosen, and then you have this estimate. This is true. So we look at what if y is not in C alpha. These are rigorous steps of the. So if y so what you have is something like this. You have this is x. So you are choosing a y in x plus eta, x minus eta. Now this is in some part of 0, 1. And if y is a point in C alpha, then this is what we have explored. If y is not in C alpha, it is possible. Okay? So if y is not in C alpha, let us estimate this. Okay? Let y belong to I stable. This is clear. It has to be somewhere here. Okay? Nj with 1 less than or equal to j less than or equal to 2 to the power. That is it. So without loss of generality, we assume mod a minus x is less than mod b minus x. What does it mean? It means the following. Suppose x is here, x is in C alpha. Okay, so you have the interval A. Okay, the interval is this. So we have chosen what is that? Y belongs to this. So if x is some point and what you have is okay, this is your. So we assume that x, the distance between x and A is less than the distance between x and B. Now if you are on the other side, you can work in a similar way. So that's the assumption that we do. Then we assume it again. Modulus of this, because you know that the point x is in C alpha, so this is equal to mod Fy divided by mod y minus x. Now Fy is given by, this is equal to mod y minus a whole square sin 1 upon y minus a. This is the definition of the function divided by mod y minus x. Now this is less than or equal to mod y minus x, because this is what you call minus y minus a whole square divided by mod y minus a. So you have, this is less than or equal to mod y minus x, which is less than. So you can make it as small as you please. Therefore, the derivative exists. Okay. Therefore, therefore, what you have is this, that equal to 0. Hence, or what you call the limit of this, as x tends to C alpha is what you call the derivative. The derivative exists. And this is equal to what you call Therefore, it follows that f derivative exists everywhere and f mod f derivative of x is less than or equal to f ab at, and this is bounded by 3. That is easy to compute. So you work out the derivative of this and estimate it from this term. So that's estimated. It's a bounded derivative for every x belonging to 0. So what have we proved? We have proved that f derivative exists everywhere, but an f derivative is also bounded everywhere, and that's a estimate. From this estimate, this is what we infer. Now what is to be shown? Our claim is that this is not continuous at the end point, as it is clear here. Because look at this term. It is not continuous because you see, as extends to a, this term goes off to this bounded term, and this oscillates. Therefore, it doesn't go to 0. Okay, so that's the problem. So f dash is not CR. So to see this, fix let be arbitrary. Now choose y belongs to C alpha, y not in C alpha, such that less than delta. This is possible. And also you have f derivative of y, which is equal to f derivative of +1 or -1. So you can choose this two. 3 conditions. Mod x minus y is less than delta. That means you are, suppose this is your x is in some point, then there is a y that you choose, which is y x you fix in C alpha, but y not in C alpha. And now you see that there this function oscillates very rapidly, and that's the one that you are making use of, and such that f derivative of y is actually f derivative of this, and this you see that this is in the neighborhood, this the relevant portion is this one, which fluctuates between -1 and +1. Okay, so look at that. Now here we have used a factor. See, you can choose an x minus y, mod x minus y less than delta, and y not in C alpha. That is possible because we have assumed that this is possible because we have C alpha, no vertex. What is the meaning of that? C alpha is nowhere dense means in C alpha there is no open interval completely contained in it. Therefore, you get such points. That is the explanation. And you see how we have proved that C alpha is lower dense. Earlier we have done that. So you can just recall that. Therefore, f derivative of AB, so because it is lower dense, f derivative of AB fluctuates infinity often n points please refer to the picture that you have. Near here and here f derivative fluctuates. This is the f derivative, the definition of f derivative. And the fluctuation is within +1 and -1 because it is the fluctuation of this term that happens. Thus, see, whenever C alpha is an endpoint, there is no problem. This is obvious. But otherwise, we need a proof. And there would be minus of that kind of. Therefore, what you get? Thus, f dash is not continuous. On C alpha, and we have already shown that lambda of C alpha is equal to alpha, which is positive, which implies which is positive. So I think I earlier said something like 1 minus alpha. So this is I think it has to be 1 minus alpha probably. Therefore, it implies f derivative is not numerical. Let me just check for a moment about C alpha. Okay, it is alpha, not 1 minus alpha. So I think earlier I made some mistake. Somewhere I made some statement that it is 1 minus alpha. Please correct it. It is alpha. Okay. Therefore, what we have obtained is a function capital F, which is not, its derivative is not continuous at all points in C alpha. But the points in C alpha, the lambda of C alpha is alpha, which is greater than 0, which implies f prime is not Riemann integrable. So what have we got? We have constructed a function f with the property that f derivative is not Riemann integrable. Therefore, how can you have a relation of this kind? fb minus integral 0 to a to b dt. This is ruled out, not possible in this case. Well, of course, we are taking a, comma b belonging to beta. This is not possible because this is not Riemann integrable at all. That's the problem. Okay, so the fundamental theorem of calculus breaks down here. So we have achieved our target, namely constructing a function which is continuous, for which the derivative exists everywhere, but the derivative is not Riemann. That completes the exploration of that. So we see that the fundamental theorem of calculus cannot be taken for granted in the realm of Riemann integrability. Okay, so this is the moral of the story. We have explored this subject in sufficient depth. Okay. So what next? There are other problems. So let us explore. We look at the problem of integration of term by term. Now, Fourier, when the Fourier series came on the scene, Fourier assumed tacitly that the series can be integrated term by term. Okay, and with further experience, one finds that this is not something that can be assured in all cases, or under what conditions this is possible. And this is the question that we are asking. Or equivalently, so the Fourier assumed or that the Fourier series can be integrated term by term. Well, it's something like this. See, you have a series f of x equal to sigma, something like this. We find our summing level 0, 1, and it is convergent pointwise. Okay? So assume it converges for every x. Now the question that you ask is this. Right? Is this true? Equal to is very true. What does this mean? This means the following. See, the problem is the following. See, this is true. See, formally this is it. Integral 0 to 1 fx dx equal to integral 0 to 1 Yeah, I am not changing anything at all. And it's a convergence. This is now what you are doing is interchanging the integration and the summation. So we are writing this sigma this is what you mean by term integration and then sum. So actually what you have is integral of the sum is the integral of the sum equal to the sum of the integrals. That's the question that you are asking. Or can you freely interchange the summation and the integration? Now you know that if this is a finite sum, if it's a finite sum, then this interchange is possible. But when it is an infinite sum, is it really possible? Now this is one of the questions. So if this is a finite sum, then one can interchange the sum and the integration. The integration and the summation. So the question that you have is this: is it possible when it's an infinite sum? Is the interchange valid? When the summation is an infinite sum. This is the question. Equivalently, what is it? Now you know that. I just want to draw your attention to these stats. What exactly you mean by sigma an as n tends to infinity? So we are looking at the series. What is this? This is actually, this is equal to limit n tending to infinity of Sn x. S equals, where Sn x this is it. That's the meaning of it. Okay? So, and here you know that integral this is possible because it's a finite sum. Therefore, the question that you have is this: is this possible? Limit n tending to infinity is this equal to integral Are they equal? This is the question. Okay. So this is an equivalent formulation of the problem. So you can frame it, reframe the question from series to a sequence. Okay. So we will frame it that way. So now let us formally start writing this. So it is actually the question of interchange of the integration with limit operation that you are working in for the sequence. So we will start. So let Fn be a sequence of Riemann integrable functions be a sequence of Riemann integrable functions on an interval. Let Sn tends to infinity for every x. That means you are assuming the sequence is point-wise convergent. That is, the sequence is point-wise convergent to a function f. Okay, this is the assumption that you are making. What can you say about the integral? Can we say that f is Riemann integrable? On AB and limit n tending to infinity Is it possible to say? Or when it is possible to make this assumption, or is it possible to make this statement under all circumstances? That is the convergence, the point-wise convergence of Fn. Does it guarantee that the integral also converges? Okay. So there are two questions here about the limiting function. The limiting function, is it first of all Riemann integrable at all? If it is not Riemann integrable, then there is no question arising. Okay. So is it Riemann integrable at all? So the first thing is that it has to be Riemann integrable and the limit should exist, and that should be equal to the limit of the integral should be equal to the integral of the limiting function. So here actually there is the interchange of limiting operation and integral taking place. Okay. So look at these two operations. There are two operations. See, when you deal with infinite sums, this is, or limits, this is something which cannot be taken for granted at all. And that is where I think we will start now looking at some examples to give an insight into this problem. Okay? So this is not something that can be assured always. So let's start analyzing some examples. Always working on examples gives you insight into the problem. Let us see. Look at this function. So we define n e to the power minus nx for x belonging to 0, 1, a well defined function for n equal to 1. Now each fn is integral. Because each such function is bounded by fn is bounded by n. It's a bounded function. It's a continuous function on the interval 0, 1. Therefore, it is a Riemann integral. There's nothing. One can easily get that they are all Riemann integrals. Now, if that is so, what next? Okay. So you can actually compute. So what is the limit of this is the question. So you see that this is equal to 0. This is equal to what happens? Yeah. This is actually n divided by. Now you see that you can show that this actually goes to 0. Okay. So you can show that this is actually equal to, so this is equal to 0 for x belonging to what? Need some work of playing around on this. Okay. This is actually, if you look at this as a variable, okay, right? As n tends to infinity, we look at n as a variable. Then what happens is you have a term that goes to infinity, you have another term that goes to infinity. Okay? So it's the limit of this. And this is equal to 0 for every x on the interval 0, 1. And at the end point, what happens with this function? At the end point, that is at x equal to 0, the sequence is n, therefore this is equal to. So what about fx? Fx is this function. Now what about integral 0 to 1? Now this is equal to minus n (0 to 1), which is equal to 1 minus e to the power minus. Okay, and therefore the limit of this goes to 1. Therefore limit n tending to infinity of integral 0 to 1 f prime equal to 1. What about fx? Fx is 0 everywhere except at this point where it becomes infinite. So it's an unbounded function. So the function f is not, but the function f in fact f is not defined at x equal to 0. Therefore, the limiting function as such is not Riemann integrable. So it cannot be. So this is a place where you cannot interchange the limits and the integration. Hence, integral 0 to 1 is not defined. Therefore, the question of equality never arises in this case. Okay. Now we look at another example. The first example. Second example. Second example is we know that the set of rational points on the interval 0, 1 is countable. Therefore, you can enumerate them. So let the rationals on the interval 0, 1. This is possible because is countable. So that is that. Take that as an enumeration. Now we define the following. A sequence of functions defined for every n one that is at these points r1, r2, etc. we define the function fn as R2 Rn, you define the function to be 1, otherwise 0 if x belongs to on the complement of it. Okay? Now, what does this function tend to? Now, you see that easily this function is Riemann integrable. Why it is Riemann integrable? It's a bounded function, first of all. Okay? And just discontinuities only at finitely many points, which is a null set, and therefore it is Riemann integrable. So each Fn is Riemann integrable on Q1. Okay? What about the limiting function? So let us define limit right. Okay, this is so there is a change in the previous one, that is the limit n tending to infinity fn x equal to 0 for x belonging to 0, 1, and otherwise. Right. So this is equal to, and what about this? This function is in fact the characteristic function of q intersection 0. What is it? This function is 1 on this set, otherwise it is 0. Okay. Now let us work out the integral. Integral 0 to 1 fn x dx, this is equal to 0. Why it is 0 for every? Because you see that the function is 0 everywhere except only at finitely many points. So it is 0. But what about this? Again, f is not Riemann integrable. This we have already seen. So in this case, what you have is limit n tending to infinity this is 0. This is not equal to does not exist. That's the problem. Therefore, in both these cases, you see that the limiting function is not a Riemann integrable function. Now let us explore this further. So what we have to ask is this. This is about these examples. It is quite easy to see, because one of the problems that you see here is both these examples. You see that the interchange of the limit and the integration is not possible. So in both these examples, limiting function which is not Riemann. Therefore, the interchange of limit and the integration is not valid. Now we give some sufficient conditions for this operation to be valid. State that the theorem which takes care of both these. Okay, so we look at this problem, a sufficient condition for the interchange of of limiting process, limit and integrate. Okay, so we write down the theorem. Let be a sequence of Riemann integral functions on AB and let converge to F uniformly then F is Riemann decoupled and integral A to B Now let us see the crucial condition that you have is uniform convergence on the interval AB. What about the examples that we have looked at? If you take the first example, you see that the function converges on the interval on 0, 1, it converges. There is no problem at all. But at 0, the function becomes unbounded, goes to infinity. The function goes to this. Therefore, you see that the function is not uniformly convergent. What do you mean by uniformly convergent? Okay, so the thing is this: given epsilon positive, there exists n such that this is the condition that we need. Now this should be true for every x belonging to. This is precisely what fails to happen in this case, in the first example. In the second example also you can see that this actually fails to happen because you have got, see, at finite set of points Fn is 1, otherwise 0, and as n becomes larger and larger, it spreads from a finite set to an infinite countable set. Still you can prove this result. Okay, so check this one. What the uniform convergence. So in both these cases, this will happen. So we just list out the outline of the proof, this theorem, and then stop. Okay. So we just outline it. Now, uniform convergence implies the limiting function bounded. There also the limiting function is bounded, so it's not Riemann. Now look at this one. Now consider the set. So let En be the set of points is not continuous. On now you see that in the first example there is the function is continuous. Probably the limiting function has problem. Okay, and then show that. Okay, now you write E as the union of infinity. That is the set of all points where the function is discontinuous. Show that is a null set, and this would imply so you see that this condition is satisfied on in the first example. In the second example, it is not satisfied. So you can see this. Now the third part is show that so these are the three steps that you have to do, and I leave it you to explore the proof of this. Okay, so that is the. I think this is the right time to stop, and thank you very much. I will continue with this further.